As we go through these definitions, let me know if any of these concepts remind you of a project you are currently working on or have worked on. Now we'll be discussing about optimization and training dynamics. The learning rate in Ultralytics or in an ML model controls how big a step the model takes each time it updates itself. Think of it like walking downhill toward the bottom of a valley, blindfolded, one footstep at a time. When you take huge steps, like a learning rate of 1.0, and you keep overshooting the bottom, bouncing back and forth, sometimes it's so bad you never get closer, you just get worse and worse. Take tiny steps, a learning rate of like, let's say 0.00001, and you will eventually get there, but it takes forever and you might run out of training time before you arrive. Take medium step, like a learning rate of 0.01, and you make a good, steady process of progress toward the bottom without overshooting. In Ultralytics or in machine learning model, so let's take a look into the learning rates. Let me undo this. No. Let's get this out. Okay. So let's get an arrow. This should not be like this. Let's get this. And let's get another arrow. So let's assume that this is the hill we are talking about. Let me get a free and sketch. Oh no, let's get this tiny one and let's kind of let me just delete this. So let's duplicate this. Oh no, duplicate. So like I said, let's assume that we have like a learning rate here of like LR is equal to 1.0, which is too large. Let's say we have another one as LR is equal to 0.00001, and let's assume that here we have a learning rate LR is equal to 0.01. So what happens here is, if we start here, right, and since we have a high learning rate, this can lead to moving from year to year, and also when it tries to adjust itself, it might also go back and start from here again. So it is moving, it is like moving away from the actual predictions that it needs to. So which means the error is getting higher. And for us not to forget, we are trying to, this is like our loss, we are trying to measure our loss. So normally it should move from here. Let's say even if it starts from here, it should, if it moves from here, it says that if it moves from year to year, it says that the error is still large if what it's trying to predict is here. So it will say that, okay, let me go back here or go back and keep going. But now that we have too high of a learning rate, it makes it harder to actually converge. So, and let's assume that we have a very slow learning rate. So let's say it starts from somewhere like here, from year to year, it goes again from here to this place, it goes again from this place to this place. So now see this, where it has to do it like 1,000 times, it is too small. So that leads to two tiny steps. Let me add a comment here. This overshoots and in turn diverges. But here now, this takes tiny steps and which means it is too slow. But let's now take this for example. So this, it's able to move from year to year. It says that, oh, it is getting close to its prediction year, or it's the end year. And to add some more context here, this is what we call like a loss mountain or a loss bowl. So it is an intuition, like we just need to build that mental model that, let's see what our model is trying to learn or predict as something that has to move from point A here to point B. But like we said, if we have too high of a learning rate, let's say this is 0, this is 1. If we have too high a learning rate, it goes too fast, right? And it makes it harder for it to get to this endpoint here. But if it's too slow, it would go bit by bit, which means it takes tiny steps. But in this instance now that we have like a good start, something in the middle, it goes from here again, it goes here, it goes from here again, it goes here. So what does that mean? It means that it's our model can make sense and adjust itself while it is learning. So in Ultralytics, the LR0, which is the learning rate, is the initial learning rate, and LRF would be the final learning rate. Let's go back to our presentation. It will be the final learning rate which is as a fraction of the first learning rate, the initial learning rate. So in Ultralytics, like the learning rate 0, which is the initial learning rate of 0.01, is a good starting point for a lot of data sets based on experiments that a lot of scientists and engineers has done over time. If your loss explodes immediately, reduce LR0 by 10 times. If training stalls after a few epochs, like try an LR scheduler. So we are going to get to using this model.train from Ultralytics. So we now need to talk about learning rate schedulers. So learning rate schedulers, and for us to discuss about this, right? So instead of using the same step size each time, from what we can see here, like let's say 0.01 continues with 0.01 and so on and so forth. So the learning rate scheduler allows it to adjust over time, which is a process called cosine annealing. Let me put this here. Cosine annealing. So Ultralytics using cosine annealing by default. And what does that mean? It means instead of using the same step size the whole time, even if we start with like 0.01, or even if we start with big steps, this process gradually shrink them over training. It starts fast to make big progress early and slow downs as we approach the minimum so that we can learn precisely. So let's look into like a mental model for that. So let's have this. Let's get like an arrow. Adjust. Okay, so let's get this once again. No. So let's assume that this model starts with big steps, right? What cosine annealing does is, and Ultralytics does it by default, it allows it shrink over time based on the data and what it needs to learn for it to take tiny steps towards the end. So even if it starts big, the allow scheduler allows it to shrink towards the end to make the model, or to avoid the model from overshooting. So that is it for the learning rate scheduler. Again, it is just an intuition behind it. So, and some of the context that we have to discuss more about is overfitting in like object detection. In cases whereby you discover that your mean absolute precision, training mean absolute precision, the training MAP keeps climbing, and the validation MAP plateaus or drop, you can consider things like adding more annotated data, right? And we also need to discuss about something more, which is the batch size. And let's go back to our board. So the model does not look at your entire data set at once. It looks at a small batch at a time. So let's assume that, okay, let me just get this. No, let's undo this. Let's assume that I have like, let me get a banana. Let me get an apple. Okay, then let's make this duplicated. Okay, what's okay? Command D. No. So let's assume that we have 8 bananas and we have 5 apples. And this, again, just the intuition behind it. And this is what we want to train our model on. So what the model does is it picks a small batch at a time. So let's assume that these bananas are like 100 and these apples are like 50. But in this case, let's say one banana has 20 now. So what it does is that if we set a batch size to be like, or let's just proceed with what we have. So if we set a batch size to be like 2, what it does is that randomly it takes like, let's say 2 bananas to check, or even if we have an image and an apple and a banana in an image. So it takes 2 images at once, learn from it, goes to the next 2, learn from it. So what does is that the image sees like 2 images in this case. Let's say we have a batch size. Let me put this here. Batch size. Or let's say we have batch size of 8. So even let's say we have a batch size of 8, what it does is it picks, or let's proceed with a batch size of 2, so to reduce confusion. So it picks the first 2 images randomly, computes the gradients, updates the weights, then repeats for the next 2, then repeats for the next 2. So and let's say we have how many here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is like 14 images in total. So what does this mean? This is when we now have the concept of an epoch. And what is an epoch? An epoch is the total amount of images divided by our batch size. So let's say batch size. So in this instance, we have 14 divided by 2. Our batch size is 2, right? So that means the model goes through 7 steps before an epoch, a training step, is complete. An epoch is complete. So 7 steps of going through all the images or data size according to batch size is equal to an epoch. So on a free Google Colab GPU, which is like a T4 GPU with 15 GB GPU memory. So a batch 16 works reliably for, let's say, 640 pixel images with YOLO V8 or YOLO V11. So, but if you get a code out of memory error, reduce the batch size to 8. So it would train your data, it will train your model with your data, but takes longer time according to our Epoch calculation. So we'll still discuss more about other things like the Adam optimizer and so on and so forth. But to continue, when it comes to overfitting, when the box loss converges, the box loss we discussed previously converges, but the CLS loss stays high, we need to that means the model finds objects but misclassifies them. So there might be some inconsistencies during annotation. However, in cases whereby the models detect well on scene photos but fails on new photos, you might have to increase your data augmentation. And what is data augmentation? It means creating several variants of your data along with annotations, right? So that your model can see several variants of several objects to learn from. And if your loss never decreases from the first epoch, from epoch 1, you need to do things like checking your data sets paths and annotation formats. It is usually a path error. So if this mental model helped you clarify or understand some things about computer vision models, supervised learning in general, hit that like button. It helps me know which topics are hitting the mark, and don't forget to subscribe so you don't miss the next deep dive into finding our datasets on RoboFlow.